So hey everyone. So today what we are going to study is a very important bridge for the upcoming concept that we are going to study. I mean, this bridge connects our up till mathematics to something really important of linear algebra, which is the basis and ranks. So imagine I tell you that you are currently at this position A and you have to go to position B, and this is suppose 751 kilometers away, right? And after that I tell you to reach position B there is another way. If I call this position C, so from A to C you go to suppose 506 kilometers, and then from C to B, uh, let it be suppose 800 kilometers. So did I actually give you new information? So this simple question leads to one of the most important ideas in all of the machine learning, which is linear independence. So what exactly is linear independence? To understand that, we first need to know what basis is. So basis we'll again cover in the next part, in which we'll learn more about basis and rank of a matrix, right? So initial thought of a basis is, you can think of it as a set of vectors with which we can represent every vector in the vector space by adding or scaling something to it. Suppose if I talk the most basic basis vector, it is this x and y. So basically 1 0 and 0 1, because with these basis vectors, one second, I'll just remove this. Yep. So with these basis vectors we can represent the whole we can represent like the whole, like the every vector in this vector space, right? So these are the basic vectors. Now if we have to call something in linear combination, what we can do is, like, so suppose we have V, which is a vector space, right? And we have a finite number of vectors, suppose x1 x2 till xk, and they all belong to vector space V. Then every this x, suppose I call it V, which is present in V, in the so every vector present in the vector space of the form, you can think of V equals to lambda 1 x1 plus x2 plus lambda k xk belongs to V. So this lambda 1, lambda 2, lambda k all belongs to R. So this is what we call a linear combination of vectors x1 x2 till xk. So just like the zero vector, which we have the zero vector, so it can be written as a linear combination of k vectors. Like if I write I equals to 1 till k 0 xi, so which is basically 0 x1 plus 0 x2 till 0 xk, right? So we'll get 0 only. So when are we calling something as linearly dependent and something as linearly independent? Right, because till now we have seen what exactly is a linear combination, right? Now we'll talk about what is linear dependence and what is linear independence. So like if there is a non-trivial linear combination such that we are getting 0 equals to lambda I xi with at least one lambda I not equal to 0. So at this so with this condition we call it linearly dependent. Okay, and if we get a trivial solution, that is lambda 1 equals to lambda 2 equals to lambda k equals to all our zeros, then we call it as linearly independent. So if you want to call something as linearly dependent, at least one of the lambda must be not equal to 0, and if we are calling something linearly independent, all lambdas are 0. Okay, this is for linearly independent, and this is for linearly dependent. Then, like, if I give you an example, suppose this and this, right? So this vector is basically just addition of these two. suppose A, B, C. What we have got, C equals to A plus B, right? Um, so basically C is dependent on both A and B, right? Because if you see the lambdas here, both are 1. Hence, we are getting a non-zero value of lambda. Hence, C is a dependable vector. It's linearly dependent. So if I talk about the properties, then first property of yeah. So the first property is that k vectors are either linearly dependent or independent. K vectors, if you have either dependent or independent, actually linearly. So the second property is that if one of the vector is 0, then they are linearly dependent, and same holds if two or more are same. So if one of the vector is 0, they are linearly dependent, and same holds with two or more are same. So, like what this statement means is basically a set of vectors is linearly dependent if you can make a zero vector using a combination of them, like with coefficients not all zeros, right? So, like if one vector is a zero vector, so like 1 dot 0 is 0. So the set is automatically linearly dependent, right? If two vectors are the same, so suppose 1 dot v plus minus 1 dot v equals to 0. So the set is automatically linearly dependent. So whatever a set contains a zero vector or a duplicate vector, it's linearly dependent. So next is that a linear dependence occurs when one of the vector is a linear combination of others, right? So as I told you, right, suppose x3 equals to 2x1 plus 3x2, right? So this vector is a linear combination of two vectors. So they are linearly dependent. Now to check linear independence, we again do Gaussian elimination. So we write all vectors as columns of matrix A. Okay, so like suppose this is A, then we write all the vectors here, and then we perform Gaussian elimination using the row echelon form. We can also use reduced row echelon form. Okay. So also one more thing is that the pivot columns that we have, that is the columns which have the pivot element in them, so they indicate vectors which are linearly independent of the vector to the left of it. Okay. Also, now talking about the non-pivot columns, they can be expressed as a linear combination of the pivot columns. So like if I take an example, I have 1 3 0 1 0 0 2. So if I talk about my pivots, this is the pivot and this is the pivot. So these are the pivot columns. So C1 C2 C3. So what I can say is that so C2, this is non-pivot column, and these are pivot columns. So pivot columns are linearly independent, and this is linearly dependent. That is, we can express C2 as some lambda 1 C1 plus lambda 2 C3. We can express this as a linear combination of C1 and C3. So yeah, so from this we can like say that pivot columns are generally linearly independent, and non-pivot columns are linearly dependent. Now, if I give you another example, if we take a dimensional vector, x1 as 1, 2, negative 3 and 4, x2 as 1, 1, 0, 2, x3 as 9, 2, 9, 2, 1, 1. Okay, and now we have to check linear dependence. Linear dependent. So are they linearly dependent or not? So to solve this, as I mentioned that we need to create a matrix A in which all the vectors will be acted as columns. So we'll write the matrix. So it will be 1, 2, negative 3, 4, 1, 1, 0, 2, negative 1, negative 2, 1, 1. So this will be our matrix, and then we'll convert it into either REF or RREF, whatever whatever you are able to create. So I'll create the REF form. I'll just directly write it. So it is 1, 1 minus 1, 0, 1, 0, 0, 0, 1, 0, 0, 0. Yeah. So if you see the pivot elements here, this is the pivot, this is pivot, and this is pivot. Now, since all the three columns have pivot, so that means that all the three are pivot columns. It has three pivot columns. Since it has three pivot columns, all the three columns are independent of each other. Hence, since the columns are independent of each other, so one of the condition that we used to check for linear independence, sorry, for linear dependence, was that we should get 0 when lambda I xi for I equals to 1 till k for any lambda at least, like for at least one lambda which is not equal to 0, right? But here since all the three are pivot columns, so we can't get any such solution. So the only solution that we'll get is lambda 1 equals to lambda 2 equals to lambda 3 equals to 0, which is also a trivial solution. Hence this thing is linearly independent. Now suppose we have k linearly independent vectors. So k linearly independent vectors, which I'll write in the set B or the matrix B, in which it has B1 till Bk. So, and this forms the basis for some vector space V. Now we define m new vectors, and now we define m new vectors x1 till xm as linear combination of bi. Right. So basically, x1 will be equal to summation of I equals to 1 till k of lambda I1 bi. Similarly, xm will be equal to lambda m1 till bi. I'm sorry, it will be lambda im till bi. I equals to 1 till k. So basically what our B equation looks like is this, like B1, B2, B3 and so on. Okay, and what our lambda j looks like is so lambda 1j, lambda 2j, lambda 3j, like that. Okay, so B we multiply with this we multiply with this, and so on. That's how we came up with this thing. So basically xj will be equal to nothing but B lambda j. Now to check whether x1, x2 till xm are linearly independent, we'll again check what condition we had is 0 equals to summation of lambda I xi, right, from I equals to 1 till k. So this condition must hold true. So if this is linearly independent, then lambda 1 equals to lambda 2 equals to lambda 3 equals to 0 yeah. So this condition must like hold true if we have to call it linear independence. So instead of lambda, let's write it psi. So basically summation of j equals to 1 to m psi j xj equals to 0. So can we write that lambda 1 equals to lambda 2 equals to lambda m equals to 0? Can we imply that? Let's find out. If we can imply this, that means it is linearly independent. So now let's from what we got here, let's substitute it. So instead of xj, I write b lambda j. So summation psi j b lambda j equals to 0. Right? Now what I can do is I'll just move b out. So this lambda j equals to 0. So this means that either this is equal to 0 or this is equal to 0. Now this is our B matrix, so this can't be equal to 0, right? Hence the only possible solution is that this is equal to 0. So lambda j this summation this equals to 0. So if this is equal to 0, thus x1, x2 till xm are linearly independent only if lambda 1 till lambda m are linearly independent. Okay? Yeah. So if I give you example, we have suppose b1, b2, b3, b4 all belongs to in dimensions. So I can write x1 as b1 minus 2b2 plus b3 minus b4. x2 I'll write as minus 4b1 minus 2b2, nothing in b3, and plus 4b4. x3 I'll write as 2b1 plus 3b2 minus b3 minus 3b4. And x4 I'll write as 17b1 minus 10b2 plus 11b3 plus b4. So the question is, are x1, x2, x3, x4 linearly independent? Again, I'll write the condition, what was it for. So lambda I xi equals to 0, I equals to 1 till k. So this was the condition. Now let's check. So first I'll just write down my matrix. How will my matrix look like? So this is my vector. So I will write it as 1 minus 2, 1 minus 1. Since the vector acts as a column of our matrix, okay, then second will be minus 4, minus 2, 0, 4, and 2, 3, minus 1, minus 3, and then 17, negative 10, 11, 1. Okay, then what I'll do is convert it into either a row echelon form or reduced echelon form. So what I'll get is 1, 0, 0, negative 7, so 0, 1, 0, negative 15, 0, 0, 1, negative 18, and 0, 0, 0, 0. So I have pivot here, pivot here, pivot here. So what I have is 3 pivot calls and 1 non-pivot column. Now this means that this is our dependent. Hence we won't be able to call it linearly independent since we have got a non-pivot column here. Yeah. So why ML cares about this? Suppose we have age and our birth year, right? So imagine a machine learning data set. It has features of age and birth year. Do we really need both? No, one determines the other, right? Since birth year equals to the current year minus your age, right? They are redundant, and this is linear dependence in disguise. So why is this important? As I told you, we have PCA, feature selection, embeddings, dimensionality reduction. A huge amount of machine learning is really about finding the independent information, removing redundancy, compressing information, keeping only what matters. And that's where linear independence comes into play. Linear independence sounds abstract, but it's really just a fancy word of asking, is this information actually new or it still exists? So again, vectors gave us data, matrices organized the data, vector spaces gave us structure, and linear independence taught us how to identify truly unique information. Next video, bases and ranks, the smallest set of vectors capable of representing the entire space. See you there.